Hello everybody and welcome to Chapter 1 of Python for Everybody. I'm Charles Severance, I'm your instructor, and I welcome you to this class. The basic goal of this class is to teach everybody how to program, regardless of your background. You don't have to be a math whiz, you don't have to be a computer expert, no matter how old you are or what your background is, we want to teach you how to program. So welcome to the course, welcome to Chapter 1. So the first thing to understand is that the purpose to learn to program is because computers want to do things for us. They are built and created and designed, and their hardware is set up so that they basically ask us, what do you want to do next? If you grab your phone sort of does nothing until you tell it what to do. It waits for you. And it's just waiting for you, and all the hardware, computer technology around you is generally waiting for you. And we can use this for useful things. We could play video games. We could have it help navigate for our cars. Someday we might even have self-driving cars. And it's really, in a sense, in my mind, silly if you spend your whole life not really understanding this technology. And I think it's important that we learn to tell these computers what to do rather than just let them increasingly control our lives. And so, as we'll see, computers aren't very smart on their own. We humans are the ones that imbue them with knowledge, but we need to learn to speak their language. It is much easier for us to learn to speak their language than it is for them to learn to speak our language. Although, with these cell phones, we're starting to see little bits where they can begin to understand, but you would be amazed at the 40 or 50 years that it has taken us to understand how to build programs to begin to understand. So I'm bringing you into something where you are going to learn the ways of programming and the ways of the computer, because it's easier to teach you how to program than it is to teach this how to work in your world, even though ultimately the goal is to get this to do work for you. So part of what I'm trying to do is move you from a user perspective where you just look at the computer as something that someone else has constructed and you are the user of, to the point where you construct new things. Now the first kinds of things that you're going to construct are actually things to solve your own problems. And it's very popular now to work on data, and Python is an excellent programming language for data mining and data analysis, and that's a lot of what we're going to do in this course, although really it's a gateway to all kinds of things like, artificial intelligence or gaming or navigation or mobile applications or entertainment, all kinds of things. But first we have to learn to program. We have to move from using the computer as a tool to using the tools within the computer that allow us to change how the computer sees the world. So there's a couple of reasons that you might want to be a programmer. Some of you are looking to improve your career, to be paid to work on programming. I've been a paid programmer most of my life, and I like it. It's a good job. You don't have to stand in the mud. You don't have to lift things. You have to use your brain. And I'll just say that it has been nice for my career to not be exposed to the elements, but to be able to work often wherever I want. But that's actually our secondary goal. Our first goal is to get you to write programs that solve problems that you have to solve. Maybe you have a job as an accountant or a lawyer or something else, and maybe you run across some data. Maybe there's some system that logs your time and it's not quite giving the report that you want to give. And so you say, could I just grab the log data myself and write a program to do some analysis to say, oh, what's the average this versus that, or the average of some other thing, right? And so that's the basic idea, that you'll initially use computers to serve your own ends. That makes it a lot easier to write programs because you don't have to worry about, a million users using your software. If it works for you, then we're happy. And so it takes a little more training to write software for other people or for thousands and thousands of other people. And so part of what I want to do is I want to change your perspective. You look at this from the outside and you see it from the outside and you click on things. I want to turn this around, and I want you to be the person inside this looking out at the world. And as a programmer, we are making things inside these computers for the world. And so we want to pull you into being part of this. We want you inside this, or thinking inside this. And what you learn is that if you're inside this computer and you are taking your instructions to build programs to be used by the human, oops, almost dropped that, the human outside the computer, you have things that you need to take advantage of. There's things like the central processing unit, the memory of this system, the network connection of this system, the disk drive or permanent storage on this system. And as a programmer, you are kind of mediating between all those internal resources that this has that are not very smart but highly powerful, and mediating with what that user wants, right? And so we take the end user, and we programmers, we serve the end user, but the computer serves us. So together, between us and all the computer's resources, we can serve the needs of the end user. And we do this by writing code or programming, okay? And what is that? Well, programming is a sequence of instructions where we are giving instructions to the resources inside the computer in a way to accomplish the goals of the end user. And remember, sometimes we are our own end user. It's not just you're not always doing a startup, you're not always writing a mobile gaming system. Sometimes you're writing something for yourself, but that's okay. So sometimes you're writing something to solve a problem. You're like crafting, you're doing something that you could do by hand or manually, and you're making some clever little 25 or 100 line program, and you're putting that in. Other times, like when I work on the open source learning management system Sakai, it is my creativity. I've got an idea and I want to share it with 1 million users, and so I write my code for an external audience. And so code is that sequence of instructions that the computer itself doesn't know how to hand a roster out, but I can write code that will hand a roster out by looking at the data that's inside this computer, inside this application. And so if you think about programs, we have programs for computers and programs for humans. And a number of years ago, now sooner or later this will be me showing my age, this is an example of the Macarena. And the Macarena is a song that effectively is a sequence of instructions. You put your left hand out, you put your right hand out, you put it on the shoulder, you wiggle, 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 and you spin around and you do things. And this is a program for people. And so I want you to take a quick look at this and see if you can find anything wrong with this particular program. So look really closely. So I'll show you. It's got some typographical errors in it, and we as humans are really good at reading or hearing typographical errors and correcting them automatically and instantly. And but computers are not. Computers are extremely literal. If it saw this ham instead of hand, it would think, what's a ham? And why am I going to hit someone in the back of the head with a ham? And why would I take my left hand and hit somebody? That's, these are all bad things. But the computer is going to take us very literally. And so we have to be really precise. And the computer just doesn't know the difference between what we mean and what we say. So we have to be very precise. And this is one of the great frustrations that people have when they first start using computers. And so we have to get this right. We have to get these little bits of text exactly the way they are. Computers will blow up with syntax errors, and they seem to make quite a fuss when you make the tiniest of errors, but you'll get used to that. I mean, that's not because you're bad or you're less than awesome. It just means the computers can't compensate when you make small mistakes. And so you got to get used to the fact that the computer is sort of intellectually not as strong as you, and so it gets confused really easy. Even though when it gets confused, it says seemingly mean things to you. So you'll get used to that. Okay, so the first thing I want to do is I want to throw up some text, and I want you to, while this text is up, I want you to count the number of each word in this text and tell me what the most common word is in this text. Okay? So here we go. Okay, so I kind of made that hard on you on purpose by moving it around and distracting you and confusing you. But even if it's not moving at all, it's a little bit, tricky to do. You probably stare at it a couple of times. Your brain is going back and forth and back and forth. And so text analysis is one of the great things that computers are very, very good at. And some of the things that, they can translate text, and that's because they've looked at a lot of information. So looking at text is actually something computers are really good at. And so if we take a look at the kind of programs that we're going to write to do this kind of thing, this is something that humans are not naturally good at, but computers are super good at. Now, I'm not going to have you look at this code. This code you will understand in a few weeks, but basically this is a set of instructions to open a file, read that file, read all the words in the file, create a histogram of all the words in the file, and then search through that histogram to find the most common word and tell us what the most common word is in the file. And in this clown file, the word the is the most common. It happens 7 times. And here's another large file called words.txt, and the word to is the most common thing. And our goal is to get to the point where you can write this on your own. So you can say, you know what, I got a problem to solve. That is, what's the most common word in this file? I know how to start, and then I know how to finish. I know how to do the stuff in the middle, and we have to learn this kind of weird language, but when we do, we can count millions of words as easily as you count 20 words. So that's the fun of all of this, is to teach you this language so that you can solve that problem so that you don't have to solve it. Because you could solve it, but it's not something that you're naturally good at, and it's hard work. So up next, we're going to talk a little bit about the hardware architecture that you're going to be experiencing as you write programs. Hello and welcome back to hardware architecture. Now you might ask, why do I tell you about hardware architecture? Probably you're not going to build any hardware, although it's fun stuff to do, and if you're going to become a computer scientist, which most of you won't want to be, it's a great thing to study, and those who build our hardware are amazingly talented individuals, and it's a really rewarding job. The reason I like talking to you about hardware is because I want to be able to use words at some point and say, oh, secondary storage, or central processing unit, or random access memory, or peripherals, input devices. And I want to be able to say those words, and I want you to be able to understand them. And so I'll start with a little piece of hardware called the Raspberry Pi. And the Raspberry Pi is a cute little single board computer. As we go forward, these things are smaller and smaller and smaller. And the interesting thing is that the architecture of these stays the same, but the number of components drops. So I'm going to start and give you a block diagram of sort of a generic computer and tell you the major parts of it. Now, I'm going to show you some really old hardware, some really new hardware, and then some hardware that is of medium age. And the medium age hardware is probably the easiest one to see. The architecture is the same, okay? And so the basic block diagram is that the brains, if there are brains in computers, which there really aren't, the software is the closest thing computers have to brains, but in hardware, the closest brain the computer has is this, called a microprocessing unit or a central processor unit. And this is designed 3 billion times a second to ask the question, what do you want me to do next? And these little pins on the back are our instructions, like 32 or 64 of these pins. 3 billion times a second, we send an instruction into these things. Now, we can't sit there and talk to it. We can't. And so the instructions we store in what's called the main memory. And this memory is really fast. And the memory sort of feeds this. And so every time the CPU needs a new instruction, it asks the memory where that instruction is. And so the memory feeds the instruction to the CPU does it, says give me another instruction, CPU does it, gives me another instruction, and that is the basic essence of programming. This asks what's next, and this is where your program is stored, or a program you purchased or came with your hardware, where that's all stored, and those are your places. And so you end up inside, your programs end up inside this memory. So then there's so in software you tend to program the CPU, and if you had bought a desktop computer a number of years back, it would have this thing called the motherboard. And the motherboard is called this because it kind of connects all the components together. And so if you buy memory by itself, it does nothing, but it has a place to plug into the motherboard. And if you buy a microprocessor, it has a place to plug into the motherboard. And if you buy a hard drive, this is a really old hard drive, it has a place to plug in on the motherboard. And so the motherboard sort of connects everything together. The hard drive is secondary storage. Now, the way how secondary storage is different than the main memory, which, there it is. I got unpile this stuff. So this main memory is really fast, but as soon as you turn the power off of this memory, it sort of vanishes. And so to store files like word processing files or text files or whatever, you got to store it on something that lasts a little bit longer. And so that's the purpose of the secondary storage. It's permanent. When the power's off, it stores it. Now this one here is in such bad shape that isn't probably storing anything, but it's got these little heads and it spins around and goes in and out. And we'll have a video later that shows you one of these things that's not quite in as bad a shape. If you look, this has 4 different platters that are all spinning around. And so this is just using magnetic material and electronics that sort of magnetize and demagnetize this stuff. And if you look at a disk, they're often rated, physical disks are rated in revolutions per minute, and that's how many times this thing spins around. And if you got an old desktop and you hear it spin up, this is the thing that's spinning. And it's the place that your operating system lives, your files live, your applications live, while they're stored and while the computer's turned off. And then they're loaded into this while they're running, and then this CPU takes the data from the main memory, and your program runs at 3 billion operations per second. So, let's talk a little bit about something that this is probably from the 1960s or 70s. This actually has, if you're an electrical person, it has capacitors. Those little silver things are capacitors. These little colored things are resistors, and that's more capacitors. And then there's wires, and wires move everything. And so when you say like this has millions of transistors, oh wait, that isn't a capacitor, that's a transistor. That's a transistor. When you say that this here has etched, and if you look closely at this, go look at a picture of a microprocessor online, you will see that it has millions of these. And so the difference between 1960 and today is this circuitry of capacitors, resistors, and transistors has been microized and put onto this. It's using a photographic process, and they're tinier and tinier and putting more and more on. And if you think going from millions of these to one of these is crazy, the thing that's happening now, and the reason we have whole computers inside our pocket, is that everything, all of this whole thing, CPU, memory, everything, all of it connected, and the storage is being made smaller and smaller. And so this little single board computer called a Raspberry Pi has one thing in it, and it has the main memory, and it has the CPU, it has connections for things like peripherals like keyboards and stuff. Now it doesn't yet have secondary storage on it. The secondary storage gets plugged in right here via USB. And then if you take it one step farther to my phone, it's got the secondary storage built right in. And so, you know, this picture goes from the size of cabinets in the old days all the way down to really tiny. But at the end of the day, inside it is a highly sophisticated piece of circuitry that asks for instructions one at a time, and main memory that holds the instructions and feeds them. Okay? Central processor does the thinking. Let's take a look here. Central processor does the thinking. It runs the program. It's asking what's next. It's not really smart, but it's really fast. And so we compensate for the lack of intelligence of this thing by us writing really good software that runs really fast. And so voice recognition on things like phones is possible because computers have so much storage and they run so fast, and the algorithms that do voice recognition are finally starting to work. Input devices like keyboards and mice and pens and whatever, they come in. Output devices are like the screens that we see. The main memory is the fast part of the computer that stores all the programs, and the secondary memory is the permanent storage. Increasingly, secondary memory. Do I have any USB sticks in here? I don't. Well, increasingly secondary memory is flash RAM or static RAM with no moving parts, and so you, in a few years, you'll not even be able to see secondary memory with moving parts. But that's okay. It's still secondary memory. It's still memory that lasts. And so you, and where your place is in here, is you live in the main memory. This is you. You are here. And so, in a sense, when the CPU asks the question, what next, it is your job to answer that. And you answer that by writing Python code. And so your Python code, you'll write a file in Python code, blah, 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 blah. And then that Python code sort of gets loaded into main memory. There's a magic translation process that happens. And then your code is actually answering this question 3 billion times a second. 3 billion times a second, you're sitting there. But this is you. You're really out here, but you then write a file, and the file's loaded in, and then the file runs. And that's how things are at. And that's your place in the world. Now, what's actually running is not Python code. There is, as I said, a translation process. You write a Python file, and then Python itself translates this into the actual language known by the microprocessor, which is a series of zeros and ones called machine language. Someday I would love to teach you a class on machine language, but for now we're going to teach you Python, and we're going to use Python as a crutch. We don't have to talk machine language, but you could, if you really wanted to, you could know how to write machine language. But I assure you, Python is far easier to learn than machine language. So Python acts as a translator, translates what you're doing into machine language, and then the machine language is what's sent back and forth. But still, even though it's translated to machine language, it's you. It is you answering those questions, and that's what a program is you pre-storing your response to the what next question over and over again. So here's a couple of videos that you can look at on YouTube about a CPU. These CPUs, and it looks very much like this CPU that I've got with me, these CPUs have extremely high heat. When you put this thing, or your computer, on your lap and it starts to heat up, that means it's thinking really, really hard. And so this is a small little old video from a long time ago that shows what happens when you take out the cooling capability of microprocessors and just how hot they can be. And the other video that I have is a hard disk, something like this hard disk that I have, except that it works and they turn the power on. Some of them last for a few seconds, some of them last for a few minutes. It's never I must be allergic to this hard drive. Or maybe it's because there's dust in this hard drive and I keep spinning it and I sneeze. But basically, some of them last for a few seconds, some of them last for a few minutes. It's not a good idea to open them up, but I'm glad somebody opened it up and then did what they did and then recorded it so we can all enjoy what it is that they're capable of doing. Okay? So that's a quick introduction to hardware, mostly so that I can use those words going forward. Now, what we're going to talk about next is communicating in the language Python. That is, writing code and putting it into the computer so that that can execute. Okay? And welcome to my video that shows how to get started and install Python on Microsoft Windows. Okay? So it's not too hard. We're going to both install Python 3 and we're going to install text editor. And so I'm just going to go into Google and I'm going to say install Python 3. And my top link is downloading Python. And there is my link for downloading Python 3.5.2. This version of my class uses Python 3. I have an earlier class that you may have seen that uses Python 2, but in this class we're going to do this. Now it might take you a while to download this. I've actually already downloaded it. Now the other thing we need is a programmer text editor. And you can really use any programmer text editor. We've used Notepad Plus in the past. We've used JEdit in the past. I like Atom, Atom.io, Tom.io, mostly because it works the same on Windows and Mac and Linux. But you can really use any text editor that you like. Just don't use Word or text edit that comes with the operating system. You need a programming editor that doesn't mess with weird characters or weird lines or strange formats. You must have a real programmer editor. And so I've already downloaded this as well. And so I won't waste the time waiting to download it, but let's go ahead and do the installation. So these things ended up in my downloads file. So I'll go to downloads and I'll start installing Python 3.5.2. Now it's going to ask me some things. Add Python 3.5 to the path. Yeah, that's a good idea. Install the launcher for all users. I'm going to add that. Maybe you will, maybe you won't do that. It's going to tell me where it's going to install it. Install now. Of course, it's going to ask me for permission to do these things. And now it's running through the installation. Okay, so there we go. You could maybe click on this online tutorial and documentation. But we're just going to close this. And I'm going to start and run the Windows command line. Now, you may have all kinds of fancy ways to run Python, but I like running the command line, command. I like running the command line because it's after a while it's important to know what folder things are being run in. And so here's this command line, and I should be able to type Python here. And so now I'm in Python 3.2, and this is the chevron prompt here is the Python interpreter, where it's asking for Python commands, and I can say print hello world. Of course, this is what we tend to print all the time. I can make a mistake. I can say blah, blah, blah. Right? And it'll complain to me. Now to get out of this, I can either type Control-Z or quit. In this case, I'm going to type Control-Z, and I'm back to the prompt. A couple of things. I can do a dir to see what folders and files I have, and that is like my desktop. And then the cd command tells me where I'm at in the folder. That means I'm in the users directory, Dr. Chuck. Okay? So I have now installed Python. I ran the Python interpreter to verify it. I said print hello world. Okay, and so now what I'm going to do is I'm going to actually install Atom. I already had this downloaded, so let's go ahead and install Atom on my computer. Okay, so Atom is now installed and it's kind of telling us what to do. I'm going to actually just close all these windows, close this window, close everything, and I'm going to create a file. I'm going to say print, in this case, let's see if I can make this bigger. I can make it bigger. So I'm going to type print hello from a file. Okay. And I'm going to save this. I'm going to say File, save as. And what I'm going to do is I'm going to go to my desktop, and I'm going to make a folder on the desktop. I'm going to call this folder py4e. So I now have a folder on the desktop. Move this here. I'll move this here. Oops. And I'm going to go into py4e, and then I'm going to name this file first.py. And you'll notice that when I save this, it syntax highlighted it. That's one of the nice things about a programmer editor. Okay, and so it says, oh, it's got a suffix of .py, so therefore it knows that it's supposed to look pretty with Python and make this one color, make this another color. The other thing that you'll notice is that I now have a folder called py4e. And if I'm in this command line, let me just start that up again. I'll show you how to start the command line again. Command. Now, if I do a dir, I see the folders that I'm in, and one of the folders that you can see here is the desktop folder. So I'm going to say cd desktop, and then I'm going to type the dir command to see what folders are in the desktop. These folders are the same as these folders. These things are kind of virtual folders. py for e is py for e. Now I can type cd, which stands for change directory, py for e, and I can do a dir, and now you see first.py, and that's the same as if I'm diving into this folder. Here's this file, first.py. Windows hides the suffix, which is somewhat annoying and frustrating, but that suffix is there, that file is there. And so for me, one of the things you got to figure out in Windows is how to make sure that you are in the same folder, users, Dr. Chuck, desktop, py4e, and that's the name of this file, and here as well. And now I'm going to run this program. I'm going to type Python first.py. And you see that it ran the Python code. Okay? Another way you can do this is you can type first.py. And that's because this file association has happened in Windows. This doesn't work in Macintosh. This only works in Windows. That all files with .py are expected to be Python, and it knows the Python interpreter where to run it. Okay? And so I've got Python 3.0 installed, and that gets me started, and so I hope that this little introduction about getting things started and writing your first Python program has been helpful to you. We're going to actually download and install Python 3 from python.org on a Macintosh. If you, your Macintosh for years has wonderfully come with Python 2. So if I type Python ---- version, then if I type that, I see that I've got Python 2.0. What we want to do is, in addition, install Python 3. One of these days, Macintosh might upgrade their distributed version of Python 3, but there's so many things inside Mac that depend on Python 2. I'm going to expect that it will always be named Python 3, which is what we're going to call it in a second. So here I am at the python.org downloads, and I'm going to download Python 3. You click here, and I've actually got it sitting here in downloads already because I always do that. And so, I'm going to install this. There is the installer. I'm going to say continue, continue, continue. Of course I agree. I read all that really fast, and now I'm going to install it. Okay. So now that means if I run a terminal, so this of course is start run terminal. So Python 2 is still there, but Python 3 is also now there. So we should have Python 3 installed. So we installed Python 3.6, and so there we go. And that's all it takes to install Python 3 on the Macintosh. So let's write our first little Python program. I'm going to, I like Atom, and so I've got this Atom editor. It's atom.io. Right here, atom.io, download and install the Atom editor. I like it because Atom works the same on both Windows, Mac, and Linux, and it has syntax highlighting, and so I really like things like that. So I'm going to make myself a simple Python program. Hello world, like we always do. Now you'll notice that it's not syntax highlighting yet, but I'm going to do a file, save, oopsie daisy, file, save as, and I'm going to go into my desktop and I'm going to make a folder called py4e. I'm just going to call this hello.py. Oh crud. Got to rename it. Rename it. I ended up with 2 dots. Hello.py. There we are. And so now I'm here and I'm in my home folder. I can go in my desktop and I can go into that new folder I made, Python for Everybody, and I can see the files. Now there are ways to run this, and I really want you to learn the terminal so that you really know what you're doing. And so here we are in the folder that has the Python, and then all we do to run it is we say Python3 hello.py, and there we go. And of course this is Python 3 because I'm using parentheses there. So instead of double quotes. But Python 2 is still there, and of course if you just run Python hello.py, it'll be a syntax error or not. Must be they added something. Yeah, because Python is still version 2, but apparently they allowed print in the latest version of Python 2. So away we go. Okay, so again, thanks for watching. I hope this was helpful to you to get Python 3 installed on your Macintosh. Hello and welcome back to Python as a Language. You'll notice that I'm wearing a hat. Part of the story of the hat is that where I work here at the University of Michigan School of Information, my office is in this building called North Quad, and we call it quadwarts sometimes because it's sort of got a square. It sort of imitates an Oxford quad, and so it seemed to me to evoke notions of Harry Potter. And when we first moved into the building, I joked in one of my classes that we should have a sorting ceremony for all the students as they come into North Quad for the first time. And so that was cool, and I thought that I would belong in Gryffindor, like everyone wants to be in Gryffindor, right? They're the good guys. And my students told me that I couldn't be in Gryffindor, that I had to be in Slytherin. So you'll see me drinking tea throughout the course out of this teacup. It's my Slytherin teacup. I picked that up from Harry Potter World. I went down to Florida and visited Harry Potter World. And the reason that I was sorted by my students into Slytherin is also because I teach Python. And Python is like a snake. And so if you think about the people from Slytherin, they are capable of talking to snakes. And the class that we were doing the sorting was a Python class, and so it sort of made perfect sense that you would have to be in Slytherin if you were the Python teacher. And of course, your name is Charles Severance, and then that sounds kind of like Severus Snape, and so I just accepted that I'm in Slytherin, okay? So you all can be in Gryffindor, but I can't. I'm in Slytherin. So I'm the bad guy, or the good guy, depends on how you look at it, right? And so what I'm going to do now is I'm going to, bring you into Slytherin as well, because I'm going to teach you the Python language. Python is the language that we Pythonistas talk. It was invented about over 20 years ago by a fellow named Guido van Rossum, and away we go. Now, even though I'm using this whole snake Slytherin thing, it turns out that Python was not at all named for Harry Potter, because Python was invented, almost 2 decades before Harry Potter was created, and it wasn't for the snake. It was actually Monty Python's Flying Circus was the inspiration for Python. the name Python, and because Guido van Rossum really wanted to create a programming language that, while it was powerful underneath it in its very nature, was a very powerful language, he wanted it to be a language that was fun. And he wanted it to be a language that was approachable. And so that's why Python recently has become so absolutely popular. And it's easy to learn. But it's also powerful, and that's sort of the magic of Python, is the ease of learning it, the brevity of the programs, the shortness of the programs, and the power. And so we are going to become Pythonistas. Now, as you learn to be a software developer using the Python programming language, you are going to encounter syntax errors. And I remember when I used to get syntax errors, and I remember my first programming class, and I would type on cards. And I would upload those cards to the computer, and the computer would say, "You're not worthy." And I'm like, wait a sec, those are pretty good cards. How could you be so critical of me? I'd say syntax error. And I really got sort of a really bad attitude that somehow this computer didn't like me, and that I would make cards, it would complain, and I would make changes to the cards, and it would still complain. And I'd make changes, and it would still complain. I'm like, how can I win in this situation? And you're going to feel the same thing. You're going to absolutely feel the same thing. You're going to be struggling. You're going to be like, how come this computer hates me? Let me assure you right now, the computer doesn't hate you. The computer actually loves you. It just is not very good at showing how it loves you, or telling you how or why it loves you. And so syntax errors are not so much Python telling you that you're bad, or that you're an inadequate programmer, or you should find something else to do. It's really Python's admission that it doesn't understand what you're trying to say. And so you got to get used to that. And it's frustrating, but you got to get used to the fact that syntax errors are your friend. Python is saying, hey, I got to line 7, and I was doing fine up to line 7, but boy, in line 7, there's some little thing. I don't know what the word else means in this context, or you didn't indent it, and so I'm kind of confused. What did you mean? Please, please, please help me. And so it's so much easier for you to learn Python than it is for Python to figure out what you mean when you're writing code. So we have a number of different ways to sort of encode our instructions when we talk to Python. One is we just run Python interactively on our computer. Hopefully by now you've got it installed, and you just type Python at a command prompt. So either a Windows command prompt, or a Linux command prompt, or a Macintosh command prompt. And I got some examples of how to sort of get this all started, get Python installed, and away you go. Now you'll notice when you run the Python interpreter, the 3 chevron prompt, Python is asking you what next, right? This is you, it's saying, I want to talk to you, I want you to tell me some Python to do. If you know the Python language, you know what to say right here. Now if you know Python, you can type these languages. You can say, oh, x equals 1, which really means go find a little piece of memory, label it x, and stick 1 in it. Print x is like, go find that thing where you labeled it x and bring me back that number and tell me what I stored in there. Now, why you want to do this, that's a different question. And these are very simple things. It's going to take you a while to get the big picture of why we're doing this. So just trust me that you want to learn these statements, and then later we will successfully turn those into a program. So x equals x plus 1, the third line there. X equals x plus 1 is not, as it seems in math, it basically says, hey, go grab the old value of x, add 1 to it, and stick it back in x. That's what that means. So the equal sign really has kind of an arrow to it. And then we say, hey, go look up that x thing that we just did and print that out, and then we're going to say quit. So that's us talking to Python. Now, you can type just about any crazy stuff you want in here, and Python will be unhappy and talk to you. So what we're going to do next is we're going to start talking about the actual language of Python and what it is that we have to say to make Python happy when we're talking to it. So now we're going to start learning the actual Python language. So what do we say? You can think of this as almost like writing a story. we're going to start with a basic vocabulary. We're going to talk a little bit about lines or sentences, and then we're going to start talking about how to put those sentences together to make a coherent paragraph, as it were. And you just have to accept the fact that when I start teaching you this stuff, it's not going to make sense for about 6 or 7 more chapters. And so just sort of bear with me, except, I mean, I remember when I first learned, it went from me confused. Holy mackerel, this is awesome. And so I expect many of you will go through that same thing. So just learn the first parts, accept the fact that it doesn't necessarily make sense in a big picture, and just bear with us, okay? So we'll start with vocabulary, we'll start to make sentences, and then we'll have little short stories and paragraphs, okay? And so this is a short story about how to count the words in Python. It's got a couple of paragraphs, and we are going to look at all of this stuff eventually. So we start with a set of reserved words. And what are reserved words? Well, they're words that Python expects when you use these words that they're going to mean exactly what Python expects to mean. And what it really means is you're not allowed to use them for any other purpose than the purpose that Python wants. It's sort of part of the contract. It's like when you have a dog and you go, what did you think of that television program? And the dog has no idea what you're saying, and then you say, do you want to wait until Saturday to go to the veterinarian? And the dog still doesn't know what you say. And then you go like, how would you like to take a walk? And then the dog goes, walk. I know what that means. And then hits the door, right? And so the way the dog sees you is blah, 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 walk, blah, 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 food, blah, 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 treat, blah, 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 walk. That's kind of how Python looks at these reserved words. When you say class, it goes class. Oh, I know what that means. Now, if I say zap, it's like, oh, zap something that you get to decide, or it's maybe a variable name. So reserved words are simply words that when you use these words in Python, and there's only a few of them, like and or del, or if maybe, pass maybe, in. A lot of these, you won't end up using them. It's just these are reserved for Python and part of the Python vocabulary. This is Python vocabulary. Now, when we move from words to sentences, you see that Python is a series of lines. A Python program is a series of statements. They have an order because the computer wants to know what next, what next, what next. So what next is start at the beginning. So I already talked about an assignment statement that basically says x equals 2. This is not a mathematical statement. This is a directive to say, take this variable 2, this value 2, this constant 2, and stick it in a location in your memory, and remember that I asked you to name it x. X is a variable, something you made up. You chose that. And so, but it's Python's job to remember it. So this says, go to whatever that x is, there's a 2 in there. Now pull that x back out, add 2 to it, which makes it 4, and stick it back in x. And so that makes this a 4. So x is a 4. And print x says, go look up that thing that was an x and print it out. And so these are like, each line has something to it. I'm using a reserved word. Well, actually, that's a function, but it's a reserved word too. And so there's reserved words and all these things, and you combine these. There are operators. Plus is an operator. Equals is an operator. These things do things, and we'll learn all this stuff in time. So the basic building blocks of lines of Python. Now, as we take these lines of Python and build them up, we end up making paragraphs, programming in paragraphs. And so one of the things that it's important is I showed you how to do interactive Python. So you just type Python and you type a statement and a statement and a statement. Those get really tiring after about 3 or 4 lines of Python because you start making mistakes and you have to start over. So the better thing to do is to, as your program gets a little larger, to write a script. Put your Python instructions in a file and then tell Python to read from the file and then run the script as it's entered in that file. We tend to name these files with .py, and I've got a series of videos that you can watch to figure out how this all works. Like I said, you can type interactively to Python, and it's a great way to experiment with Python, check to see if a statement does what you think it does, but script is the way. after we are past 1 or 2 lines of code, we write it in files and then run it separately. So there are a couple of basic patterns, and it's really important to understand each of these patterns. And like I said, we'll teach you these patterns separately, and then we'll combine them together. And when you combine them together is when you say, oh, that's what a program is. So you have to suspend disbelief. We have a couple of different patterns. One is a sequence of steps. Do this, then do this, then do this. Conditional is like skipping something. Repeated does it over and over and over again. Computers are really good at repeating stuff, much better than people. People get tired going over and over doing the same thing. And then we have store and repeated steps as well. And so if we take a look at this, and we take a look at a Python program, this is a piece of code. This is a little script. If you type this into the code, take this code, Python code, into a file and ran it, it starts at the beginning, and then it goes to the next line, and the next line, and the next line. And Python executes the scripts as you write them. So it says stick a variable to find a place called in your memory called x, stick 2 into that, okay, then go to the next one, print that out. So the program is producing output. Now go read x and add 2 to it and stick it back in x, so x is 4, then print that. This side over here, this is called a flowchart. I'm not going to make you draw flowcharts. I'm only going to draw them a few times in ways that I think will help you. But you can think of it as Python, when it finishes something, it goes on to the next one, unless you tell it otherwise. Finishes this, goes on to the next one. Finishes this, goes on to the next one. Finishes this, and now the program is all done. And so that's sequential steps. You just type them in, Python runs it. They're important, but sort of uninteresting, because you can only get so far. And you can't really make them intelligent because it's always going to do the next one. So the next thing we do is what are called conditional steps. And this is where it starts to get intelligent. I mean, where you are able to encode your brain into the computer. Like, oh, wait a sec, let's only do this step if something is true. And the syntax that we tend to use here is the reserved word if. Okay? And so the if is like a fork in the road. You can go one way or you can go another way, and you're asking a question. So inside the if statement, right here, there is a question saying, is x less than 10? That resolves to a true or false. If it's less than 10, that's true. If it's greater than 10, it's false. And so then what we do is, if it's less than 10, we have this indented block of code. There's also this colon that tells us we're in the beginning of an indented block of code. And so what it basically says is, if this is true, run that code. If it's false, skip that code. So it can either run it or skip it, depending on this question that's being asked. Now, if you look at this code, it's pretty obvious what's going on. It comes down, x is 5. If x is less than 10, that's true. So it runs this code and prints out smaller. And then it comes back here, it de-indents the next basic sequential. This ends up being kind of a block. If x is greater than 20, if x is greater than 20, oh, come back. If x is greater than 20, this turns out to be false because x is 5, and so it skips this. So the bigger never comes out, and then it continues on and prints fini. Oops, that's a typographical error. Make that a lowercase print, and then prints fini. So it comes in, runs this, skips this, and then finishes. Okay? So here is the last one we'll talk about, the repeated steps. We'll get back to store and retrieve later, but for now we're just going to talk about 3 of the 4. This is another program, and the key is that we're going to use this same choice where we're going to go in, but then we're going to run for a while, and then we'll have an exit condition where we get out. So this is a repeated over and over and over and over again, and this is the essence of how we make computers do things that are seemingly difficult, while that are more naturally difficult for people. Okay? And so how do we encode this notion that we want to do something not forever, but for a while? How do we encode that notion? And so we do it in this way. So we have our statement, sequentially go to this while. While is a keyword, and it's asking another question that's a true-false question. Is n greater than 0? I read this as long as n remains greater than 0, keep doing this indented block. And you have a colon at the end, and then you have 2 lines of code that's indented. So that tells us what the loop is, and then this is now de-indented. And so it comes in, and if this is true, it runs these 2 lines. prints out n is 5, and then it says n equals n minus 1, which makes n be 4, and it goes back up, and it goes up and it asks this question again. Is n greater than 0? If it is, continue on, and prints 4, and then subtracts it, and it does that, 4, 3, 2, and prints out 1, then it comes up, and now after this, n is now 0, n is now 0, and n is no longer greater than 0, so it takes sort of the exit ramp and goes down here. So it takes the exit ramp and goes to here and runs the next line. Now, we're going to cover all this again. So I'm just trying to give you the big picture. Next couple of chapters, we're going to hit all these things again, and we're going to hit them in much more detail with a lot better information. This is now sort of like combining these. And again, I don't want you to really like know this stuff. You will know this in a couple of weeks. You will see this program again. But this shows you how we combine those patterns of repeated, sequential, and conditional together. And so this is a bit of sequential code. Comes in here, runs this, which happens to ask for a file name. Then it opens the file. It creates a data structure called a dictionary. This is all sequential. Now the for is another form of loops. So this is going to loop for a while. And then this is within a loop. We can even have 2 indents, and that's another loop. So these are like repeated. And then it goes down to the next sequential bit. Then it does this. Here's another loop that's going to run, and then here's a conditional it's going to run. And then when it's all done, we print out the last thing. And this is, of course, is the program that does, it figures out the most common word and prints that most common word out. And so this is a Python short story. It reads some data. It reads the name of a file. It opens that file. It talks about how to make a histogram. And then it looks through for the most common word. So don't worry too much about this. Over the next couple weeks, we'll fill in the pieces so that you absolutely understand every single line of this code. So, this is a quick overview of Chapter 1. Stick with us. You realize it will be Chapter 7 before this makes too much sense. You really have to trust that you are learning important things and that it all makes sense when we bring it together like in Chapter 7 in a few weeks. Hello, and welcome to Chapter 2. Now we're going to continue to talk about the building blocks of Python, variables, constants, statements, expressions, etc. The first thing we have to talk about is constants. These are just things, we call them constants because they don't change. They're numbers, strings, etc. And we use them to sort of start calculations, or if something is greater than 40 hours, we're going to do something. And so 40 is the constant in that situation. So we have 123, we have 98.6, we have hello world, which is a string by enclosing it in quotes. We pass each of these things to the print function, and a side effect of the print function is that we see the output. So print 123, prints out 123, print 98.6, prints it out. So these are just really the syntax of constants, and without constants we can't write really much of anything. The other sort of foundational notion of any programming language are the reserved words. And like I said before, reserved words are these special words where Python is listening for them, and there are very special meanings. So when Python sees if, it's not just any other word, it means how Python implements conditional execution. Variables are the third building block, and that is a way that you can ask Python to allocate a piece of memory and then give it a name. And you can put stuff in that. Sometimes you just put one value. Later we'll see, when we do collections in chapters 8 and 9, we will see that more than one value can be put into a variable. And the variable, how we control the variable is through the assignment statement. And as I said before, it's important to think of the assignment statement as having an arrow to it. So this is not saying x for all time is the same as 12.2. What it's saying is take 12.2, find a place, find some memory in your computer there, Mr. Python, give it a label x, we get to choose the x. That's the variable part. We chose it, right? And then stick 12 in it. And then the same is true for 14. Go find another spot, name it y, and then put a 14 in there. So think of this as an arrow every time you see that equality, the assignment in an assignment statement. Now, these variables hold one value. So now if we have these three statements, these two, and then the third one executes. It says put 100 into X, but that wipes out the old value of 12.2, and it rewrites it with 100. And so we can change the variables. That's another reason that we call them variable. There are some names. Now, there are some rules for making variable names. You can start with a letter or an underscore. We tend not to, as normal programmers, use underscore. We tend to reserve those for variables that we use to communicate with Python itself. So when we're making up a variable, we tend not to use underscores as the first character. You can have letters and numbers and underscores after the first character, and they're case sensitive, but it's really a bad idea to use case as the only differentiator. So in this case, spam, eggs, spam23, and underscore speed are all totally legit. We would probably not use this one unless we were actually doing it because Python told us to use that variable. 23 spam starts with a number, # starts, and dot is not a legitimate variable character. And spam, capital spam, and all cap spam are different, but this is not something that you want to sort of depend on too much. So that's just the rule names. We tend to start them with a letter and then use letters, numbers, and underscores. Underscores, other than the first character, are generally pretty common, and you'll see those used a lot. Now, when we're choosing variable names, one of the things about variables is we get to choose the name. We get to choose the name X, choose the name Y. And so sometimes we like them short, but sometimes we want them descriptive. And the notion that of making variables descriptive is often confusing to beginning students. Sometimes it's really helpful to, if you're going to have a line of text and you name the variable line, that's great because the next person reading your program says, oh, that must be the line of text. Whereas it also can become misleading that the name of a variable somehow has meaning. So sometimes we'll have even singular variables and plural variables like friend and friends. And you're like, is plural? Does Python know about singular and plural? And the answer is no. So sometimes we pick variables that make no sense. Sometimes we pick variables that make a lot of sense. This is just something that you as a beginning programmer are going to have to understand, that we can pick anything we want. And so you'll see, I'll try to call attention to this in the first few lectures as we go through. So here's a bit of code with an assignment statement, two assignment statements, a multiplication, and a print statement. And you can say, what is this doing? Now, Python is perfectly happy with this code because it assigns it in there. You have said, please go give me this as a label. And then we assign two variables, and then we're carefully pulling these two variables back out, multiplying them together and sticking them into yet another variable, and then printing that variable out. That seems like, you know, we can figure out what it is. You just have to look really carefully. And a single character mistake, and Python is going to be, you know, pretty unhappy. Okay? So that's one way to write this program. It's hard, though, because any of those characters are long variables and they're random stuff. It's not very friendly to anyone who might read your program. Now this looks a little friendlier. It's the same program because Python just wants a correspondence. You picked A, you picked B, and you picked C, and it's really much easier for us to see what's going on. And so this is, in a way, going from here to here is much friendlier, but we can be even friendlier if we pick mnemonic variable names. So this is not mnemonic, this is short and convenient, this is long and inconvenient. Python is happy with any of these. Here, on the other hand, is another version of the exact same program. And now you think to yourself, oh yeah, now I get it. 35 is the number of hours, $12.50 is the rate, and then we're going to multiply the hours and the rate and come up with a pay, and we're putting out the pay. Now whoever wrote this program is helping us greatly understand what's going on. And that's good. Choosing variable names. Python, again, all three of these are the same to Python. Choosing variable names in a way that help your reader understand what's going on is a great thing. The problem is, the danger is, if you read this and you think that somehow Python understands payroll, that if you name a variable hours, that Python knows what hours means. The answer is, Python really doesn't care what you name the variable as long as what you name it, you use it, right? And so you got to be careful. And so you'll see, when I write my code in these first few weeks, first few lectures, I will sometimes write it with gibberish. I'll sometimes write it with extremely short but meaningless variable names. And sometimes I'll use meaningful variable names. and I'll call your attention to it, and it will get you. You'll start, when you look at this third kind, it has meaningful variables or mnemonic variable names. You'll just instinctively want to give Python more intelligence than it sort of deserves. I guess that's probably the best way to say that. So we've talked about constants, we've talked about reserved words, we talked about variables. And so here we have a sentence, like we've already done some of these things, where we set x equals 2, we retrieve the old value of x and add 2 to it, so that becomes 4, and then we print 4 out. Print is a function that's built in, and we pass in whatever we want to print out. So this parentheses is part of a function call. Okay, so an assignment statement, you have to really get your head around the notion that it has this arrow nature and that it evaluates this entire right-hand side before we change the left-hand side. And so you can think of this sort of as at time step 1 it does this, and then at time step 2 it does the copy. And that's how you can have something like x on both sides of an assignment statement. And so if, for example, we have x and x has 0.6 in it, what happens is that it sort of ignores this part right here and evaluates the expression. So it pulls the 0.6. Everywhere x appears, it pulls 0.6 out. Then it starts running these calculations, and then it has the new value. After all the calculations are done, then and only then is it going to put that back into x. And so it sort of takes that and puts it back into x and then wipes out the old value. At this point, this has all been taken care of, and it's been reduced down to this 0.93, and so that is what's put in as the new value. So, up next we'll talk a little bit more about making more complex expressions. So welcome back. We're now going to talk about expressions. Expressions are a little more complex calculations that we can sort of do on the right-hand side of an assignment statement. So one of the things about expressions is operators. And the operators in computer programming are often very much the same as the mathematical operators, but we don't have all the fancy characters that we have in mathematics, and so we have to choose what's on the keyboard. And then we really go back to the 1960s and 1970s, and we used what was on the keyboard in the 1960s and the 1970s to make these operators. So plus is addition, minus is subtraction. We don't have a times sign or a dot in the middle, so we use the asterisk as multiplication. Division, we can't put two things over top of each other, so we use slash for division. Raising to the power, because it didn't have little characters back then, is star star, which is raising to the power. And then remainder. Remainder is when you do integer division, it's also called the modulo operator. It's the remainder, not the quotient. And I've got a picture of that coming up. So here's a whole series of little examples of this. Right? So we've already seen, the plus, x equals x plus 1. Keep remembering that these assignments are arrows, basically. Arrow, arrow, they have a direction. Multiplication, 440 times 12. Dividing this by, that's division, over 1,000, 5.28. Here we're going to put 23 into JJ, and then we're going to do modulo. So that says, take 23, divide it by 5, and give me back the remainder and put it in KK. So this is the expression that evaluates like this. Take 23, divide 5 into 23, 4, remainder 3. The 3 is what comes back up here. Okay, and so that is the remainder. It's also called modulo operator. It turns out that for things like picking a random number and then taking the modulo of 52 is a way to pick a card randomly. So this modulo operator is actually, especially in games and other things, super useful. So that's the various operators. It's important to know which of these operators goes first. That's called operator precedence. Now normally we put parentheses in, like, so if I put the parentheses in here, I'd say this goes first, parenthesis, then this goes first. Oh, actually not that one. Whoops, got that one wrong. This happens first, this happens, then this happens. Okay, and so, but it's important for us to be able to know, if there were no parentheses, the order in which these things will happen. So the way things work in terms of operator precedence is parentheses are the most important thing, followed by raising to the power, all else being equal. Multiplication and division are all both equal. and then addition, and then within it's adding left to right. So let's see an example of how this works. And so if we take 1 plus 2 to raise to the 3 power divided by 4 times 5, and we print out what comes out of this. So the way I did this when I was taking exams back many years ago when I was first in computer science is I'd write it all down and I'd look for the highest precedence thing. Now parentheses would make this easy, but exponentiation is the first one. So that means we're going to take this, and that's going to be 8. 2 to the 3rd power, 2 times 2 times 2, 2 cubed is 8. Then what I would do is I rewrite the whole thing with the 8 there. And now I look across and I'm looking for multiplications because the power's been done. The multiplication is what I'm looking for next. And then there is both multiplication and division. They're equal. They're at the same level. And so what happens is they're done left to right. 8 divided by 4 happens before 4 times 5. And so the fact that it's not 4 times 5 but instead 8 times 4 is because of the left to right rule. So then this gets rewritten to be 2. 1 plus 2 times 5. And this one, multiplication, is the top one. So that does this next. 2 times 5 becomes 10. I rewrite it again. And then 1 plus 10, addition, is the lowest thing. And that's how we end up with 11. And so that's how I would do these problems if I ever saw the problem on an exam. And it's a fun problem to put on exams because there is one and only one answer. And every programming class has usually at least one slide about this stuff. So like I said, the rules go top to bottom, parentheses, power, multiplication, addition, and then left to right within it. So we talked about variables and computing values to put inside variables, but the one thing you've kind of also, maybe you noticed it as we go by, is we have different kinds of data. We call it type. Is this of type integer? Is this of type floating point number? Is it of type string? What is going on here? And Python is pretty smart about various kinds of types of data. And so, we're adding 1 plus 4 here, and Python knows as it looks at this that that's an integer and that's an integer, and we'll add it together and make it an integer. So that thing is an integer. We can also use this plus to concatenate 2 strings. This is hello blank plus there. And plus looks here, says, oh, that's a string and that's a string. So I know what to do with strings. I will concatenate those 2 things together so it becomes another string that gets assigned into E, and it's hello space there. The plus doesn't add the space. I added the space by putting it right there. And so these operators are kind of smart in that they kind of know what they're dealing with, and sometimes they will do one thing or another depending on the kinds of values, variables, or constants that they're working with. And so sometimes type can get us in trouble. So here we have E, which is hello there because we've concatenated these 2 strings together. And now we're adding 1. And the problem now is that it looks on one side and says that's a string and that's a number and says, I don't know how to do that. This is another one of those annoying errors that you think that somehow Python doesn't like you, but it just is confused. If you look at these things, traceback. Traceback always means I quit. It means I stopped, I ran, I'm quitting now because I don't want to go any farther because I've become confused. So your program stops running and you say, here's where I stopped running. Because we're typing interactively, it's always line 1 here. Type it, but if you read carefully and you don't get too stuck on too much stuff, line 1 that tells us something in module type error, can't convert int object to str implicitly. So that's an integer right there, and that's a string, and that's what it's complaining about, that little bit right there. If Python is so grumpy about types, then we should be able to ask it about types. So there turns out that there is, inside Python, a built-in function called type, T-Y-P-E. So we can pass into type. So the syntax is calling a built-in function named type, parenthesis is the parameter that we're passing to it. We're saying, hey, hello, tell me something about the type of the variable E. And so this is a function. The parentheses are part of the function call. And it says, oh, that would be of class string. And then we can pass in a constant and says, hey, what about hello? The string hello, it's like, oh, that's a string too. What about a 1? Well, that's an integer. And so we are asking Python through the type function what the type of either a variable or a constant is. And there are even several types of numbers, and we'll even see Booleans and others later. Like 1 with no decimal, that's an integer number. 98.6 with a decimal, that's a floating point number. And so, constants can be both integer and floating point. And I'm just asking over and over and over again, what is the type of what's in XXX, what's the type of what's in temp, and what's the type of the constant 1, and what's the type of 1.0. You can also use a set of built-in functions like float and int to convert from one to another. And so this basically says, I want to convert, oops, let's go back. I want to convert 99 to a floating point number. So this is a function and it's participating in this plus, but before it can finish the plus, it turns this into a 99.0. The difference between 99 as an integer and 99.0 is that it's a floating point number, and that actually turns this computation, as it looks to the left and looks to the right, it says, oh, I've got a floating point number on one side, an integer on the other side, and so I'm going to make my calculation overall be a floating point calculation. I can also pass into the float function. I can say, take this variable I, which has a 42, also an integer, and then give me back a floating point. So that'll be 42.0. Pass that into f. We print it out, and it is indeed 42.0, and it's a float. And so it knows the type and value in any variable. This is an integer, a value 42. This is a float, a value 42.0. Integer division in Python 2 was kind of weird, and it was actually one of the big things that they changed between Python 2 and Python 3. This is a Python 3 course, so we're not worried about that too much. What's nice about integer division in Python 3 is it always produces a floating point result. And that means that Python 3's division is more predictable and it works more like a calculator. So in this case, I mean, you can go back and look at my Python 2 lectures and see how crazy it was in Python 2. 10 divided by 2 is 5.0. And the weird thing here is these are both integers, but the division forces the result of the calculation to be a floating point number. And this, 10 over 2 could be 5. But 9 over 2 is 4.5, and so that is accurate. In old Python 2, that would give us back 4, which is completely unpredictable and weird. The same with 99 over 100. As you would expect, if this were a calculator, you get 0.99. Actually, what you get in Python 2 is 0, because it would round it down. It doesn't round at all, it truncates it. So 99 over 100 is 0.99, and then it truncates it to 0. That's Python 2. We're not talking about Python 2. There's a good reason we're not talking about Python 2. Welcome to Python 3. Of course, if there are a floating point on either side, the result is still a floating point, and the result is still a floating point. So integer division produces a floating result in Python 3.0, not in Python 2.0. That is an improvement in Python 3.0. And that's why we're recording these lectures. I have a whole great set of lectures about Python 2, and now I'm going to have a great set of lectures about Python 3. Welcome to Python 3. Okay, so we've been talking about converting from integer to floating point, but you can also convert from string to integer or string to floating point. And so here we start out with a little string value. Now it only works for strings that are made of digits. So quote 1, 2, 3 quote is not an integer. It is a 3-character string that has 1, 2, 3 as the characters in that string, which is very different than 123. We say, what is the type of this? It's a string. We say, let's add 1 to it. And it says, can't convert into string, so that blows up, right? Because this is a string. It looks to both sides. String plus an integer, not good, okay? But we can convert this. We can call the int function, which is like the float function, and pass a string in. So it says, hey, take this and turn it into an integer. So take the input of sval, which is the string 1, 2, 3, and give me back an integer representation of that, which is going to be 123. So we say, what kind of thing do we get back? Well, we got back an integer. We can now add 1 to it and get 124. And so you have to manage the type of things, and you can convert from one type to another. Now, int is not magic. If you send something into it, a string that doesn't consist of digits, then you're going to end up with another error. Invalid literal for integer with base 10, blah, 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 blah. So it's really complaining. It says, I want these to be numbers here, and you just gave me letters, so that's going to cause this to fail. Another thing that we're going to do with variables is, just like the print function takes something, a list of things, in this case, a string, comma, a variable, and then prints some output in the program, the opposite of that is input. Actually, input generally happens before output. Input is a built-in function, and we pass to it a prompt. a string of text that's going to be printed out for the user, and then it stops and waits. So it says, who are you? And then right here it just sits, waiting for us to type something. So we type blah, 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 and then hit the enter key. Right? We hit the enter key, and then this text ends up in this variable. So this is an assignment statement that Chuck is the result of the input call, gets copied into the NAM variable. So let's do that again. It's evaluating an assignment statement. Remember, it's kind of this way, or you can think of it as just do this right side first. It writes this out, writes that out, then it waits, wait, until we hit the enter, and takes this Chuck, and that becomes the result of this input, which is then assigned into NAM. Now then we go sequentially to the next line. It prints out welcome, comma, contents of the variable NAM. Now this one, this comma here, actually does put the space in here automatically. So it says welcome space Chuck. So it pulls there's no space in Chuck, just the CHUCK. And so print can take more than one thing separated by commas. As a matter of fact, print can have, a whole bunch. Oops, come back. Print can have comma, 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 parentheses, as many as you like. Everything you've seen up to now is kind of one thing in the print, but that doesn't mean that print only can do one thing. So I've talked about variables, we talked about constants, we've talked about input, we've talked about output, and now it is time to write our first meaningful program. And so this program has to do with those of you who have traveled internationally. If you traveled to the United States and you traveled outside the United States, you notice that there is an elevator convention that is different inside the United States. In the United States, walk in the ground floor in the elevator, that's 1. And if you walk in the ground floor in Europe or many other places in the world, in the elevator is 0. So we have written a small app that we're going to put on the App Store and get wealthy with called Elevator Floor Conversion App. And it's going to ask us, we're in Europe and we're lost, and you say, well, what floor would this be if I was in the United States of America? And so we have to read the floor that we are at in Europe, and then we're going to convert it to a US floor, and then we're going to print it out. This is very silly, but it is a pure essential program that has input, does some kind of task on that input, and then produces some output, which is useful for some value of useful. Okay? So let's take a look at how we combine everything that we've learned in this lecture: input, processing, and output. It's a 3-line program, but it's sort of the beginning of something that programs do. Okay, you're going to do lots of programs that do this. So here we go. Program starts. We do the input side effect. It prints out this and then waits. We type in 0. That comes back here. And the 0, which is a string. Input gives you back a string. It doesn't give you back a number. It's a little different in Python 2, but in Python 3, input gives you a string. So quote 0 quote, which is what we typed here. We didn't type the quotes, it's a string, gets stored in the imp variable. Then we move to the next statement, and on this right-hand side, we convert that string variable to an integer, so that becomes the integer 0. We add 1 to it, and then that becomes 1, and then we assign that into USF. I've named this variable United States floor, right? So imp is the input and USF, that's mnemonic. It doesn't know anything about elevators, it's just I picked a variable that was quite friendly. And so at this point, USF has the United States floor that's equivalent to the European floor, and then I just fall down and I do a print statement. Print out US floor, comma, that's this space right here, and then whatever the contents of the US floor variable is. And you could see that I could write this on 4, and it would say 3. I could write this and say 7, and it would say 6. This is an amazing program. It converts floors in a European numbering scheme. Wait, actually no, I got that wrong. Hang on, let me clear this. I wasn't thinking clearly. I could type in 4 and it would give me back 5. I could type in 6 and it would give me back 7. See, I'm confused. Haven't been in Europe in a couple of months, and so I forgot all about the floors. But that's the idea. Now, this is a super simple program, not super useful, but you get the idea that we're going to pull some data in, we're going to do some intelligent thing. Soon this will be hundreds of lines of code instead of 1 line of code, and then we're going to present the results to our user. Now, Another element of most any programming language is what's called a comment. A comment is a way for you to put in a program file some text that's to be ignored by Python or C or whatever language we happen to be using. In Python, comments start with a pound sign. So what you could do is put a pound sign anywhere in a line, and then after the pound sign, Python ignores everything after that pound sign. It can be the first character. So here's our recurring concept that we talk a lot about. We're not going to cover this. Remember what this does. This is counting how many letters. There's 16 thes, and there's in that file there was 6 twos or whatever it was. This is that code. We'll get back to this code. But what we've done here is I've added some comments that are really for human consumption. So this first paragraph is get the name of the file and open it. The second paragraph is count the word frequency. Maybe I should have said histogram here. Count the word frequency and assemble a histogram. And then here I'm putting this pound sign in, find the most common word, and then I'm all done. I print the stuff out, right? And so all I'm saying is comments are for people to read. Your next programmer or the person who's going to change your program after you're done with it. And they're nice. And you don't have to use any particularly weird syntax or variable naming conventions. You put a pound sign in and you can write anything you want from that point forward. Okay, so we've talked a little bit about variables and types and mnemonics and how we would choose variable names and how expressions work and the various operators, converting between different types, printing, input, output, and comments. So that just kind of gets us sentences. And coming up next, we'll talk about conditional execution, where we're really starting to move up to paragraphs. So see you in a bit. Hello and welcome to Chapter 3, Conditional Execution. In conditional execution, we meet the if statement. The if statement is where Python can go one way or another way, and it's the beginning of sort of our way of making Python make decisions for us. Sequential code, we just do some things. Sometimes that's useful, but now we can have our code check something and then make a decision based on that thing. So the conditional steps in Python are pretty straightforward. The keyword that we're going to use is the if statement. And so if is a reserved word. And the if statement has as part of it a question that it asks. And this is asking if x is less than 10. And the colon is the end of the if statement. And then we begin an indented block of text. And the way this works in this particular thing is this line is the conditional line. If the question is true, the line executes. And if the question is false, the line is skipped. And you can think of it the way this is, right? X is 5, ask a question. Is it 10 or not? These questions do not harm the value of x. If it is, then we run this code, and then we sort of rejoin here, and then we test this next if. And if that's true, we do this code, and then we do there. But in this case, it's going to be false because x is not less than 20, and so it just continues down here. So if we look at how this works, it runs this line. Then it sees this question, it skips that line. So this line does not run, and so smaller prints out and fini prints out. Okay, and so that's the basic idea of an if statement. And the indentation, when we are done with an if statement, we de-indent back, and there's this little block. This is one sort of if statement, and this is another if statement. And these are the two conditional lines that either run or they don't run, depending on the question, the answer to that question. So we have a number of different comparison operators that we can use to ask these true-false questions that say, is this true? So again, we're kind of limited to the keys that were on computer keyboards in 1940s and 1950s, less than or equal to. So we didn't have fancy math characters, so we just concatenated less than and equal to be less than or equal to. This double equals is the asking, is this equal to? And so that's a little tricky. The equal sign is that assignment operator. If I was building a language today from scratch, I would probably make assignment be arrow and the equals question to have an equals. Or I might say, somewhere I would say question equals. But I'm not building this language, so it's not up to me. So this is the question. Double equals is asking the question is equal to. Greater than or equal, greater than, and not equal. So this is the exclamation point is sort of like not equal. So that's sort of not equal. So that's how we do not equal. So if we take a look at some of these in some examples. All of these are going to be true because of the way x is set. If x is equal to 5, that's the question version. That's true or false. It'll execute that. If x is greater than 4, it's going to execute that. If x is greater than or equal to 5, it's going to execute that. Here's kind of a shorthand where if there's only one line in this block, you can kind of pull it up right on the same line after the equals. If x is less than 6, which it is, true, execute that. Then if x is less than or equal to 5, do that. And if x is not equal to 6, do that. Now, like I said, all these questions have been carefully constructed so that they're true, just to kind of show you the syntax of those comparison operators. Now, you don't just have to have a single line of text in the indented block, and this will be something you're going to get used to. So if we indent more than one line, then the conditional code is actually these 3 lines. So the idea is you have an if statement, you come in, you do an indent, and as long as you stay indented, you stay in that if block. If it's false, it just skips all of those. So the way this is going to execute, x is 5, we print before 5, is x equal 5, that's the question mark, and that's true. So it's going to run all these, and then come back, and then continue on in the de-indent, so all this stuff is running, right? And then it says x equals 6, well that was false, so that skips all of them. So none of these lines of code run, so these actually don't run, and it says afterward 6, so that's a mistake. Those don't run right there, okay, because x is not equal 6. Okay? So indentation is an essential part of Python. We use indentation in lots of programming languages, often to kind of demarcate blocks, to show where blocks start and stop. But in Python, it's syntactically correct. You can make an error if your indentation is wrong. After an if, you must indent. And you maintain the indent as long as you want to be in that same if block. And then when you're done with the if block, you reduce the indent. In this rule of indenting, comment lines and blank lines are completely ignored. So we're going to tend to like put 4 spaces. 4 spaces ends up being the normal thing that we do, and you'll see all the code that I write has 4 spaces for each indent. If I go in twice, I use 8 spaces. And we have this instinct of wanting to hit the tab key to move in 4 spaces. Now the problem is that it might look the same on your screen. A tab and 4 spaces might line up the same place depending on how tabs are set. But Python can get confused by that. So we tend to avoid using actual tabs in files. And so most programming text editors, like if you're using Notepad or Text Wrangler, there's a place to set the tabs to say don't put tabs in this document, but every time you hit a tab, move over 4 spaces. And so you hit a tab, but it's like space, 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 space. Now the nice thing about Atom, and this is the text editor we tend to recommend in this class, because it works on Windows, Linux, and Mac, but also because it automatically sets this up. As soon as you save your file with a .py extension, you can sort of hit the tab key with impunity, and everything works perfectly. But the key thing here is that Python insists that you get this right, and if you don't get this right, you're going to get indentation errors, and they're just another syntax error. So if you're using something like Text Wrangler or Notepad, hunt around in the preferences and you'll find something about expanding tabs, or maybe how many spaces each tab stop is supposed to be. And so you check these, and what this really is doing is telling your text editor never put an actual tab in the document, but somehow simulate tab stops using spaces. And so here is a bit of code. It's got a nested block, but it gives you this sense that you have to be very explicit when you're reading Python code of whether the indent is the same, between 2 lines the same, increased or decreased. And so every time you increase it, you mean something, and every time you decrease it, you mean something, and literally if it stays the same, you mean something as well. And so if we take a look at this, here we have a line, and the next line has the same indent. This is an if with a colon at the end, so we have to increase the indent, and now we're maintaining it, okay? So these 2 lines are part of that if, but now we have de-indented. So whether you choose to de-indent this word or whatever, where you do this de-indent affects the scope of how far this if statement lasts, right? it lasts up to but not including the line that's de-indented to the same level as the if. Okay, so this is a de-indent. Now we have a blank line, which doesn't matter, and we maintain it. Now we have a for, which we'll learn about in the next chapter, which is a looping structure. Let's do a for runs this 5 times. It has a colon, and it also expects an indented block. Now we have what's called a nested block, where we have an if and a colon, and we go in some more. So this is like 2 indents, right? So these are 1 indent, and these are 2 indents. And so this is a block within a block. And then we de-indent, so that means this print is not part of the if statement, but is still part of the for statement. And then we de-indent again, and then that means this print is sort of on the same level as that for statement. So if you start thinking about this, you want to be able to start thinking that these blocks are the start of the block with the colon line up to where the up to but not including this line that's been de-indented. So the for goes this far, right? The for goes up to but not including the line that's de-indented. The if goes up to but not including the line that's de-indented. So as you do this, you'll sort of mentally start drawing these blocks, and pretty soon you will start constructing them as blocks. And it takes a while, but doesn't take forever. But in Python, unlike other languages, you have this is very important, and it matters, and you can have syntax errors if you get it wrong, because you're really communicating the shape and structure of your code using these indents and de-indents. We already saw a nested indent. This is a nested if, so you can put an if within an if, and you can go as far deep as you want to go, like Russian dolls. And so here we have x equals 42. If it's 1, we indent 1, and then with this next thing we do, these are at the same level of indent, but now we see an if, and it has to indent further. So this is like 2 in, 8 spaces, and then we de-indent back. Actually, we de-indent back 2. And so if you watch this and you take a look at how this works, it runs to here. Oops, back up. Comes in here. The answer is yes, x is greater than 1. Prints this. Is x less than 100? Well, it's 42, so the answer is yes. So it runs this, and then it kind of continues back to there. And you can also think of drawing boxes around this. This is one if box, and then within that if box there is another if box. And again, it's the indent block up to but not including where the de-indent happens. And this here is like 2 backwards de-indents. So it ends 2 blocks. So 2 blocks are ended by where we place this. We could move this in, or we could move this out. We could have it all the way into here, we could have it to here, or here. And where we put that line depends on how the ends of these blocks are going to work out. So one form of that's a 1 branch if that we just saw, but then you can also have what's called a 2 branch if. And the basic idea of a 2 branch if is that you're going to come in, you're going to ask a question, and you're going to go one direction if it's yes, and another direction if it's no. We call this an if then else. It's kind of like a fork in the road. And the way to think about it is, depending on the output of this question, we're going to pick 1 or 2 of these, but if we pick one, the other one's never going to happen. So it's like an either or. We're either going to go one way or we're going to go the other way, but there is no path where we somehow go boot through both of them. That doesn't happen. And the syntax that we use for this is what we call the if then else. And so the first part is a normal if with an indent, and then we de-indent, and then this is another reserved word, else, with a colon, and then we re-indent. And so this is really end up being part of a whole block here, and the else is the part, this is the part that runs if it's false, and this is the part that runs if it's true. The first branch of the if, the first indented block is what runs if it's true, and the second indented block is the one that runs if it's false. And so here we go. It's just if x is greater than 2, in this case it's yes, we're going to print bigger, and then we're going to be all done. And so we do 1, and so this one did run and this one did not run. So basically with an if then else, one of the 2 branches is going to run, but there's no case in which both branches run. And again, you sort of draw these blocks around these things mentally, and in this one you sort of take from the if, not the else is really part of the block, up to but not including that print, which is back indented, de-indented back to the same level as the if statement. Okay? This Python is actually one of the more elegant languages, even though after a while this indenting, and when you get too far in, it gets a little bit complex. but this is a good way to visualize this with these indents. Coming up next, we're going to talk about some more complex conditional structures. So welcome back. Let's talk a little bit more about some more complex conditional statements that sort of build on this concept of if and if then else. The first thing we're going to look at is the multi-way branch. And so the idea is it's kind of like the if then else where you're going to pick one of two, but now we can pick one of three or one of four or one of five. And it introduces a new concept called the LF. The LF is another reserved word inside Python. And the way it works is it's probably best to look at this here where it checks the first one, and if it's a true, then it runs that and then it's done. It doesn't check them all. It's not like it sees that there are two logical conditions. It actually checks them, the first one, and how you order these matters, as we'll see in a bit. And so if the first one is true, it runs. If the first one is false and the second one is true, it runs this one and it's done. And if the neither of them are true, it falls through and there's an else clause that is otherwise, and it runs that. So basically it's either going to run one and then skip the other two, or it is going to, skip one, skip two, and then run this one. But it only runs, in this case, one of them. But the important thing is it checks these questions in order. And it doesn't check the second question until it finds that it doesn't check the second question until it knows the first question is false. So if the first question is true, you're done. You're done, and you're done with this. You're done with the whole block at that point. So only one of these three is going to execute in that block. So here's sort of some examples of this. If we, for example, have x equals 0, it's going to come down here. X is less than true. That's true. So it runs this code, and then it skips down to that. And so it's like this, runs that code, and then skips to the end. Okay. On the other hand, if it's 5, then this is false, and it skips that, and it checks this. This is true. It runs this code, and then it's done, skips to the end. It goes like false, true, run, end. And then if x is like 20, for example, it runs, false, false, run the else clause, and you're done. So skip, else, run that code, and you're done. So in this case, we ran that, and we didn't run that, and we didn't run that. Again, one of them's going to run. They're checked in order. These questions are checked in order, not out of order. It doesn't look ahead. It just checks in the order that you wrote it. You're the one that wrote that order. And so there's a couple of variations on this multi-way. You can have no else. You can have no else, as in this case. And this just means that it might not run any of them. In this case, x is 5, so it's not less than 2, but then it runs this one. But if x was like 50, for example, if x was 50, then this would be false, then it would skip, and this would still be false, and it would skip. And neither of these two would run. So if you don't have an else, you're not guaranteed that one of them is going to run, because else is like the catch-all. If the other ones are all false, then the else is the one that runs. Similarly, you can have many LFs, but this is where it's really important for you to make sure you know what order they're being taken in. So I've got, this. If this is true, it runs. It goes all the way to the bottom. If if it's false, 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 true, it runs this one and it's done. If, on the other hand, it looks at it as false, oops, go back. If it runs false, 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 they're all false, then it runs the else. Right? This one has an else. This one didn't have an else. They don't have to have them. The key is you can have more than one of these LFs. Okay? So I got a couple little things. I'll let you pause right now and look at, the question is, are there, looking at the 3 lines or 4 lines of code, x equals something. Are there lines of code that will never execute regardless of the value for x? And I'll let you pause and think about it, and then I'll explain it to you. Okay. Hopefully you paused and thought about it as long as you like, so let me now explain it to you. So we come in here, And if x is less than or equal to 2, it's going to run this first thing. And if x is greater than or equal to 2, it's going to run this. And if neither of those are true, then it's going to run this. Well, the weird thing is, all numbers are either less than 2 or greater than or equal to 2. I carefully constructed this to the point where it would never run this line of code. It is either going to run this one or run that one, but it's not going to ever run this one. So that was kind of like a weird dysfunctional one that I constructed. This other one is a little different. If x is less than 2, we do this. If x is less than 20, we do that. If x is less than 10, we do that. And if none of those are true, we do that. Well, the problem here is between these two lines. The problem is if something's less than 10, like 6 for example, it's also less than 20. So even though there might be values for which this is true, those also are going to have this true. So for something like 6, it's going to run here, and it's not even going to look at this. That's the point. It doesn't even look at this. And so I could have made this more sensible if I'd have moved this little block of code up to there. So this is where the order in which you choose your questions, the way you put these LFs together matters, because it doesn't look at all of them. It only looks as long as it can. As long as it sees falses, then it keeps on going to the next one. But as soon as it doesn't see a false, it doesn't continue. So the last conditional structure we'll talk about is the try and except structure. And if you know any other languages like C++ or Java or JavaScript, you're like, whoa, that's kind of an advanced concept. But it turns out in Python, because of Python's propensity to throw tracebacks in situations where you kind of would like to recover, it turns out you kind of have to use it a little more and a little earlier in your programming skill. So the problem is what if there is a line of code and you absolutely know it's going to make a traceback, it's going to blow up, but you don't want to blow up. I mean, I don't want to have code blow up. If you're using my autograder and you see a traceback in my autograder, that's kind of like, I consider that a failure. I could put an error like, hey, you entered blank data, or you didn't enter a number, but a traceback, that just seems like I'm too lazy as a programmer. So we as programmers are supposed to anticipate parts of our code that are going to blow up potentially based on perhaps the user's input, and then do something about it. And that's what the try and except are for. It's you take this little dangerous piece of code that might break and might blow up, and you surround it with a try and says this might blow up, and if it fails, run this code down here. Okay, so that's the try, and if you get an exception, the except is kind of like if you get an exception. And the problem is if you are running code, here's a little bit of code, we put hello Bob in and we convert it to an integer, and we know from past experience that this blows up. Right? You can't take hello Bob and convert it to an integer. It's just going to blow up. The problem is and here we are. It says, oh, you blew up on line 2. That's great. And I'm not very happy with hello Bob and whatever. But the important thing is your program stops. These other lines, they don't. Oops. These other lines, they don't exist. Right? It doesn't go any further. Remember, the traceback is Python is really confused and I don't know what to do next. So Python is just going to be conservative and stop. So Python stops and your program stops. No matter how much error checking you put down here, it doesn't matter because it's gone. It's all gone. And like I said, we take this kind of personally because the code that you write is like you being put into the computer, giving it instructions. And if the code blows up, well, that sort of wipes you out. You're not in the game anymore. You're not able to do anything. So we want to be able to, especially in these situations where we can anticipate that an error that might happen in the normal course of your program's execution might be something that you want to compensate for. And that's what the try and except does. So here's a bit of code for the try and except. And we just have 2 little bits of straight line code. And so we put a string in here that's hello Bob, and then we're going to convert it to an integer. This is the dangerous code. This code in this case with hello Bob is going to do a traceback. And so we say try, and then we indent the dangerous code, and then we add this little except bit. If it works, the except is ignored. If this blows up, it runs the except. So in this code, it's going to come in, it's going to try this. This is going to blow up, but instead of giving a traceback, it's going to say, "Oh, I've got an available except. I'm going to run this except code, and then I'm going to continue on." And so that prints out first -1. So because we set this variable ister to -1, like a little flag telling us that something went wrong. And then we keep on going, and now we have put in 1, 2, 3, the digits 123, the digits 1, 2, 3, and now it's going to work, but we still have it in a try block, and then this one works, it does not blow up, and then it ignores the except block. So the except block is only triggered when something goes wrong in the code. It is ignored if something doesn't go wrong. So it's like you bought an insurance policy on this line of code, and when things go wrong, your except block springs into action and does whatever it is that you want it to do in the case of an error. Okay, so that's a pretty useful thing. You got to be a little bit careful that you don't overuse it, because if you put more than one line inside the try part and one of the lines blows up, it doesn't come back to the try block. And so in this one here, we have kind of a simple, silly one where we set the string. We're worried about some stuff. Well, the print statement's never going to blow up, so it's a bad idea to put it in try except anyways. Then we do this conversion, and that's the dangerous part. And in this one, it's going to blow up. And so then it's going to go to the except block and then run the except block and then continue. What it doesn't do is somehow go back and finish this. So these lines are gone. So if you look at it like this works. The try starts. Hello. This blows up. It goes to the except. It runs the except, and it continues on. Never runs that code. So it's not like you took out an insurance on the whole block. Any of those lines can blow up in the block, but whichever line blows up, that is the last line that's executing in that block. Okay? So you tend to want, in this particular example, you would probably, the print statement would go out there, and this print statement would come down here, and you would only put in your try block the single line of code that you think might blow up, because you kind of know print statements aren't going to blow up. So this is an example that's a more common real-world example where the user is going to type some data. And it's users that get us in trouble. So our program starts by asking the user to enter a number, and we know that this could be dangerous. So we're going to do it. We're going to put the conversion from string to integer in a try block, and we're going to set -1 if that's a failure. And then if it's greater than 0, we'll say nice work, and if it's less than 0, well, not a number. So first time we run this program, out comes enter a number. We type in 42, which is a string. That 42 goes back into roster, runs in here. This runs, it's fine. That becomes a 42 number, so we skip the except block, and ival is greater than 0. We print out nice work, and we skip the else. Okay, so it says nice work. On the other hand, if we run it again, this time, the input says enter a number, and we're silly. We enter the word 42, but in words, 40, F-O-U-R-T-Y. So that's a string, and that goes into roster. And then the execution continues. We run in here, and now this is going to blow up. That's going to blow up. Normally, we would see a traceback right there. There'd be a traceback, but we're not going to because we put this calculation in a try and except block. It's going to immediately run the except block, set ival to -1, continue on with the program. See, you are not blown up at this point. And if ival is greater than 0, well, it's -1, so we're going to hit the else clause and print out not a number. So we've done error detection. The user set something that caused a line of our code to kind of blow up, but we put that line in a try and except block, and so we caught it. And so we dealt with that fact. So in summary, in this, we talked about if statements, we talked about else, we talked about try and except, how important indentation is to mark blocks where they begin and the end, and an else if and try except. So up next, we're going to talk about loops and iteration. Hello and welcome to Chapter 4, Functions. This is the fourth of our basic patterns. We'll get to iterations next. Functions is the store and reuse. One of the things in programming is that we never like to repeat ourselves. We don't like to, if we have 4 or 5 lines of code and we're going to do the same thing later, we don't like to put the same 4 lines of code in, even if it has to do with reliability. If you find something wrong with those 4 lines of code and you got them 12 different places in your program, then you got to find all 12 places and fix them. So like collect those to one place and then call them and reuse them. And that's the idea of store and reuse. So this is how functions work inside of Python. The first thing we notice is there is a new keyword def that stands for define function. And the def is like an if statement, or we'll see fors and whiles, that they end in a colon, and then they have an indented block, and then the indented block de-indents, and that's the end of the function. And so there's two statements make up this function. The key thing that you have to understand and get used to is this def part is actually not running any code whatsoever. It's actually remembering the code, and that's what I call the store phase. The def creates a bit of code and records it like a macro, although it's much more complex than a macro, and it names it whatever you chose. You gave it a name. We named this one thing. And so it, as a side effect of Python reading or parsing these 3 lines, it doesn't do anything, but it remembers. These 2 lines are what you would like to run when you invoke thing. So this is the definition of a function, and this is the invoking of the function. But so this doesn't do anything. So there's no output here from that stuff right there. But then what happens is you invoke it. And this thing looks like it's part of Python, but you in effect have extended Python with your def statement. And so when it sees thing, it goes up and runs your code. And so out comes hello fun. And then it comes back and goes to the next line, does print, so print comes out. And then it goes back and like, oh, this is the reuse part, but we get to reuse it. We define it once and we use it twice. Then it runs this code again and then goes to the next line and it's all done. So this little bit came out twice. And of course this is really simple so that I can fit it on a page, but you get the idea that I don't want to repeat. This might be, 15 to 100 lines of code, and I don't want to type those over and over again. So I say, hey, store these in a name that I choose, and then when I invoke them, bring them back and then run them again. Okay? So that's the basic idea. We actually have already been using functions from the beginning. The print is a function, right? Print is a function. Every time we see print, P-R-I-N-T, parenthesis, and then we have some stuff in here, we're calling the print function. This is the syntax with 2 little parentheses, is the syntax for functions. And so input's a function, type is a function, float's a function, int's a function. All these things are built-in functions that come with Python at the moment that we started. I mean, we installed Python and these came along. And then there's other functions that we define and use, and that's what the def is for. And in effect, we can create new reserved words of our own making that extend the Python language after we define the function. So it's just this bit of reusable code that takes some arguments. We haven't seen any with arguments. There's a little parenthesis, and we'll see how that works in a bit. We define using the def keyword, and then we invoke it. There's the defining phase, which actually doesn't run the code, it just remembers the code, and then there's the invoking phase. You define it once and then invoke it 1 or more times. Calling the function or invoking the function, we think of those 2 things as the same thing. Call, invoke are just the terms we use. Most people just say call the function, but invoking it is a perhaps more descriptive way to think about it. So here's an example of a function. It is built into Python. It's called the max function. And we can pass some parameters into the max function. So we pass the hello world string. Now, like much of Python, max knows what kind of thing is being passed into it, and it knows that it's looking for the largest character, the lexicographically largest character, and in this case it scans this little, that's inside the max code, it scans through and finds the largest character. So apparently lowercase letters are higher than uppercase letters because in English we get back a W, and so this is what's called the return value. So this is an assignment statement. Let me clear this and start over. So this is an assignment statement, so it has to evaluate this right hand side. And a function call is nothing more than like x plus 1. It's something to evaluate. It runs the function code, passes in this argument, and then this residual value, this is called the return value, we'll look at this in more detail, becomes the result of this little bit in the expression, and there's nothing else. We could have, w plus 1 or something, and then the w is what's stored into big. Okay, so we print big, and big is a variable that has the letter W inside of it. And then we ask what is the smallest, and that finds the blank, and so we get a blank to see this. There's a min function and a max function. Both of these are built in. These are built-in functions. They're always there for us. Okay, so here is another example of the max function, and so we can think of this as invoking or calling this function as this right-hand side is being evaluated, we are passing this variable in, and there's some code in here, and it's going to do some stuff, yada, 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 and then it's going to give us back a bit of stuff, and that's its return value, and then that goes up into the big, right? And so that's how this works. And so this is actually built in or burnt in, I guess I can't draw. And so you can think of this as sometime a long time ago when Python was being first formed, somebody wrote some code. And it's got some stuff in it. It's got a little loop that reads through all the letters. It has to figure out if it's a string or a list, etc., etc., etc. But this is store, except you didn't do the storing because it's already built in. And then this is the reuse, store and reuse. So we build these things into Python. They're already pre-built, as if before the first line of your code executes, way up here, someone put all this code in for you into Python and created a thing called max for you. Now we've been using this already, built-in functions, we've got type conversions, we've got like the float that takes a integer and returns a floating point version of that. And again, this is kind of like an expression. So it's like I want to divide this by 100, but before I do that, I've got to convert it to a float. So it has to sort of do these function calls as it's evaluating the expression. Okay? Sometimes, like here, we just have a prints out the return value. That's what this is. This is the return value. If you just type a function in a parameter, it can be in a constant or it can be a variable. And as we'll see in a second, we'll give you many of these if you like. So you can either just run it or take the result of this. This passes an integer in, converts it to a float, and then puts the float into that. Type tells us what kind of thing that is, and you can use this inside of an expression. And so it's like, what am I going to do first? Oh, I've got to do 2 times this thing. Oh, wait a sec. Pause just briefly for a moment to call out to some float code, pass a 3 into it, and then something comes back, the return value, the residual value comes back, and then that participates. In this case, it's going to be 3.0, participates in this 2 times 3.0. Okay? And so 2 times 3.0 then ends up being 6.0, et cetera, et cetera. But you can see as it's like, oh, wait a sec, I got to figure out what this is, call the function, get the return value, and then continue processing this expression. We've also done this with string conversions, partly because, just as an example, the input always returns a string. The input function returns a string. And so, here's this string, could be coming from input, but we'll just take 1, 2, 3. We know that that's a string. It's not the number 123. And if we try to add 1 to it, we get a trace back. Cannot concatenate string and integer. Trace back. But we can't convert that string to an integer. And so int can take like a floating point number or an integer or even a string, and it says, oh, I know what I'm supposed to do with a string. I'm supposed to look at this, interpret these as numbers, and multiply by 10 and figure out what the hundreds place is and all that stuff. There's a little bit of work to that, and it does it. But then it gives us back an integer, and we say, oh, what is that? That's now the 123, but it is of type int. And now we can add 1 to it and get 124. And as before from this example that we're kind of reusing from a previous chapter, you don't want to try to convert, oops, sad face, sad face. Sad face. Don't want to try to convert something that doesn't have digits using int, because it'll say, I don't know what to do, and then your program quits, right? You don't want your program to stop, tracebacks, and you can, of course, deal with that with try and accept, but that's like a previous lecture. Okay, so up next we're going to talk about building our own functions, not just using the predefined ones. So welcome back. We're going to continue and start talking about building our own functions. So again, we use the def keyword to define a function, and then later we're going to invoke this. And there's a bit to it. We are defining the name of the function. In effect, we're extending Python and creating new predefined things that we can use, except it's our code. It starts with a def keyword, has some optional arguments, which we'll see in a bit. That's what the parenthesis is. And then the name. And the function names follow the same rules as variable names. And then you have an indented block, whatever code you want to do, and then you have a de-indented block, and that sort of defines the essence. The key thing here is this is not calling It's not invoking, it's not executing, it's remembering, it's storing, it's figuring things out. So here is the output of a program that defines a function but then doesn't use it. So this is a sort of broken function. So here we go. We start x equals 5, print. You don't have to you have all the defs at the beginning. The def runs whenever. So, out comes hello. And then we define a function, and this says, oh, you want to make a new thing here. So I'll make a new thing. It's kind of like a variable in a sense. And then it copies this stuff, copies it up there, and says, later you probably are going to want to use this, so I'm going to remember it. So it doesn't do anything there. No output comes out. Then it says print yo, and out comes yo. And then it adds 2 to x, so x is now 7, and then it prints x, and there's no 7. There's 7. These print statements never ran. They never ran. Why? Because we did not invoke them down here. We defined them, but didn't invoke them. So let's take a look at how you invoke a function, right? You define it, and then you use it. Sometimes you define it once and use it once, but more commonly you define it once and use more than one time. Again, the store and reuse pattern. The def is the store, and the invoking is the reuse. So here's just a slightly different version of that last program, and so now it's going to actually invoke it. So x equals 5, print hello, def, so out comes hello. This produces, the def produces no output, right? But because there's a D indent here, that is the entire blob of the code that is part of print lyrics. So it prints out yo, and now we're going to invoke. This is the call. We're going to call the function. Now the function goes up. Let's clear this. So we're down to here. Now this like suspends at this place. It's like remember to come back to here when we're done. Go up, run this code, and then come back, and then continue on. So it like leaves like a breadcrumb of where it's supposed to come back to, and then it runs, and then the print lyrics, of course, produces the 2 lines of output, and yeah, that should probably not have. That they should be up there, and then x equals x plus 2, which makes it 7, and then prints out 7. Okay, so this is the invoke or call the function. Okay, you defined it, and then later you called it. Now, in addition to just call and return and invoking, we can pass parameters in. And the example of the parameter is in the max function, we have to say, this is the thing I want you to find the maximum of, the largest thing. And part of it is